I will introduce linear programming and the simplex method. Linear programming, or LP, is a mathematical technique used to optimize outcomes such as maximizing profit or minimizing cost under certain constraints. An LP model consists of three main parts. The first part is decision variables, which are the unknown values that need to be determined. The second part is the objective function, which represent the goal that we want to optimize, such as maximizing profit or minimizing costs. The third part is constraints, which are the limitations or restrictions in the problem. The model translates real-world problems into linear equations and inequalities, allowing identifications of feasible solutions. Next, the simplex method, developed by George Danzig, is a systematic method used to solve linear programming problems. The process starts by formulating the LP model. Then, the model is converted into standard form. After that, a simplex table is constructed and perform iterative calculations until optimal solution is found. In conclusion, linear programming defines the problem structure, while the simplex method provides the solution process.
This problem is about a juice store at the Ramadan Bazaar. The store sells two types of drink, is refresher and super tuber. Each drink uses different ingredients such as orange, apple, watermelon, and ginger. However, the resources are limited. First, we define the variables. Let x be the number of refresher and y be the number of super tuber. And next, we write the objective function. We want to maximize the revenue. So z equals 6x plus 8y. And base the ingredients given for orange, 3x plus y. 3x plus y is less than or equal to 50. For apples, 2x plus 3y is less than or equal to 40. For ginger, x is less than or equal to 15. For watermelon, y is less than or equal to 10. And x and y are greater than or equal to 0. Then we draw the graph for all constraints. Each equation is drawn as a straight line, and we find the intercept to help draw the line. The feasible region is the area that satisfies all the constraints. Next, we identify the corner points from the graph. The points are 0, 0, 0, 10, 15, 0, and 15, 3.33. Then we substitute each point into the objective function. Z equals 6x plus 8y, and the maximum value is obtained at 15, 3.33, and maximum value of Z is 116.7. And therefore, the store should produce 15 refresher and 3.33 super tuber to maximize revenue.
This slide presents maximization problem 2. Now we proceed to the solution. First, divide the variable. Let x represent the ounce of cereal A and y represent the ounce of cereal B. Next, state the objective function. Since the goal is to maximize protein intake, the objective function is z equal to 9x plus 10y. Now, consider the constraint. For the calorie requirement, 100x plus 140y must be greater than or equal to 480. For the sodium limit, 150x plus 190y must be less than or equal to 700. Additionally, x and y must both be greater than or equal to 0. To simplify the inequalities, the calorie constraint becomes 5x plus 7y greater than or equal to 24. the sodium constraint becomes 15x plus 19y less than or equal to 70. Now, let's move on solving the problem and finding the maximum protein. First, we simplify our constraint. The calorie constraint becomes 100x plus 140y is greater than or equal to 480. And the sodium constraint becomes 150x plus 190y is less than or equal to 700. After simplifying, we get linear equation that we can graph. Next, we find the boundary line and determine their intersection point. This point represents the feasible region where all conditions are satisfied. From our calculation, we identify the corner point of the feasible region 3.4, 0, approximately 3.6842 and 0. 0 is not valid here because it doesn't not meet the calorie requirement. Then we evaluate the objective function, which is z equal to 9x plus 10y. We plug in each corner point. At 3.41, the protein is 40.6. At 0, 3.6842, the protein is approximately 36.84. Comparing this value, we see the maximum protein occurs at the point 3.4, 1. So, finally, Mr. Carter should choose 3.4 ounce of cereal A and 1 ounce of cereal B to maximize his protein intake. As shown in the graph, this point lies at the optimal corner of the feasible regions.
Now I will be presenting a minimization problem using linear programming. First, let me explain the situation. A professor wants to hire two people, John and Mary, to grade paper. John can grade 20 paper per hour and is paid $15 per hour, while Mary can grade 30 paper per hour and is paid $25 per hour. Both workers must work at least 1 hour per week, and the professor needs at least 110 paper to be graded each week, and the goal is to minimize the total cost. First, we have to define our decision variable. Let's say x represents the number of hours John worked and the y represents the number of hours Mary worked. Okay, next we form the objective function. Since we want to minimize the cost, so the objective function is z equal to 15x plus 25y. Now we move on to the constraint. The first constraint is based on the number of paper graded. John can grade 20 paper per hour and Mary can grade 30 paper per hour. So 20x plus 30y must be greater than or equal to 110. The second constraint is that both workers must work at least 1 hour. So x greater than or equal to 1 and y also greater than or equal to 1. To solve this, we have to find the intersection point and identify it. From the equation 20x plus 30y is equal to 110, we find two important points. So when x equal to 1, y equal to 3. And when y equal to 1, x equal to 4. So the intersection points are 1, 3 and 4, 1. Next, we calculate the total cost at each point. At point 13, c equal to 15 times 1 plus 25 times 3, which is equal to 90. And at point 41, c equal to 15 times 4 plus 25 times 1, which is equal to 85. So comparing both values, the minimum cost is 85. In conclusion,
The professor should assign John to work 4 hours and Mary to work 1 hour because this combination satisfies all constraints and gives the lower possible cost.
Today I will present simplex problem 4. In this question, the company wants to maximize profit by deciding how many units of product 1 and product 2 to produce. Product 1 is represented by x1 and product 2 is represented by x2. First, we change the inequalities into equation by adding slack variables. Slack variables s1 is added to the first constraint, and slack variable s2 is added to the second constraint. In the initial table, we look at the C minus Z row. The largest positive value is 6 under x1, so x1 enters the solution. Then we calculate the ratio. The smaller positive ratio is 6, so s2 leaves the solution. After the first iteration, x1 becomes a basic variable. Then we check the C minus Z row again. There is still a positive value, which is 10 over 7 under x2. So x2 enter the solution. The smallest positive ratio is 7, so s1 leave. In the final table, there are no more positive values in the C minus Z row. This means the solution is already optimal. Therefore, the company should produce 3 units of product 1 and 7 units of product 2. The maximum profit is $46. Objective function is to maximize profit. Z equals 6x1 plus 4x2. The constraints are 10x1 plus 10x2 less than or equals to 100 and 7x1 plus 7 plus 3x2 less than or equal to 42. From the QM result, the optimal solution is x1 equals 3 and x2 equals 7. This means the company should produce 3 units of product 1 and 7 units of product 2. The maximum profit of 10 is $46. This slide explains the objective functions and the first iteration in QM. The company wants to maximize profits using the equation Z equal to 6x1 plus 4x2. Here, x1 represents product 1 and x2 represents product 2. The constraints show the limits of assembly line hour. In iteration 1, the initial basic variables are select 1 and select 2. From the C minus Z row, x1 has value 6 and x2 has value 4. Since 6 is the largest positive value, x1 enter the solution. Next, we perform the ratio test. 100 divided by 10 equals 10 and 42 divided by 7 equals 6. The smallest positive ratio is 6, so select 2 leave the solution. The pivot element is 7. This slide shows iteration 2. After pivot, x1 becomes a basic variable and a new solution is obtained. From the C minus Z row, x1 equals 0, x2 equals 10 over 7, select 1 equals 0, and select 2 equals negative 6 over 7. Since x2 still have a positive value, the solution is not optimal yet. Therefore, x2 enter the solution. Next, we perform another ratio test. 40 divided by 40 over 7 equals 7. And 6 divided by 3 over 7 equals 40. The smallest positive ratio is 7, so select 1 leave the solution. The pivot element is 40 over 7. After pivoting again, S2 becomes a basic variable and the final solution is obtained. From the C minus Z row, x1 equals 0, x2 equals 0, select 1 equals negative 1 over 4, and select 2 equals negative 1 over 2. Since all values are 0 or negative, the optimal solution has been reached. Therefore, the optimal solution from QM is x1 equals 3, x2 equals 7, and the maximum profit is $46. This means the company should produce 3 units of product 1 and 7 units of product 2 to achieve the maximum profit.
I will present simplex problem 6. This question is about crumb and custard bakery. The bakery produced cakes and pies using flour and sugar. The objective is to maximize profit. The objective function is z equals x1 plus 5x2, where x1 represents cakes and x2 represents pies. The contracts are flour contracts, sugar contracts, and demand contracts. First, I converted all contracts into equations by adding slack variables. Slack variables are S1, S2, and S3. This is important because the simplex method uses equations instead of inequalities. This is the initial table. First, I look at the C minus Z row. The largest positive value is 5 under x2, so x2 enters the solutions. Next, I perform the radial test. 25 divided by 5 equals 5. 16 divided by 4 equals 4. 5 divided by 0, this cannot be divided. So, the smallest positive ratio is 4. So, x2 leaves the solution. The pivot element is 4. Next, I create the second table after pivoting. For the new S1 row, the values are x1 equals 5 over 2, x2 equals 0, s1 equals 1, s2 equals negative 5 over 4, and quantity equals 5. For the x2 row, the value are x1 equals 1 over 2, x2 equals 1, s2 equals 1 over 4, and quantity equals 4. Next, I calculate the z row. Z equals 5 multiplied by 1 over 2, which is 5 over 2, and z equals 5 multiplied by 1, which is 5. Then, I calculate the C minus Z row. For x1, 1 minus 5 over 2 equals negative 3 over 2. For x2, 5 minus 5 equals 0. For s2, 0 minus 5 over 4 equals negative 5 over 4. Since all C minus Z values are 0 or negative, the optimal solution has been reached. The final answer is x1 equals 0, x2 equals 4, and the maximum profit Z equals 20. This slide shows the QM for Windows result. The QM result is the same as the manual calculation. The software also showed that x1 equals 0, x2 equals 4, and the optimal value Z equals 20. In iteration 1, x2 entered the solution because it had the largest positive Cj minus Zj value. After the ratio test, slab 2 left the solution. The pivot element was 4. In iteration 2, all Cj minus Zj values were 0 or negative. Therefore, the optimal solution was reached. The bakery should produce 4 pies and 0 cakes to achieve the maximum profit of $20. In conclusion, linear programming helps business make better decisions and maximize profit while using limited resources efficiently. From this assignment, we learn how to solve maximization, minimization, and simplex problems using graphical and simplex methods. We also learn how to use QM for Windows to check the answer and understand the iteration process. Overall, management science is important. because it helps organizations solve problems systematically and make effective decisions.